welcome to the podcast. This is Mr. White,
Mr. Johnson.
and we are recording the last podcast of the first semester. It's good.
Let's just get it done.
Let's get it done. Okay. So, today we're going to talk about impulse and how it relates to momentum. So, impulse, we probably won't think of as a scientific word, but it is a very scientific idea. And I'm going to bring back an old idea that we talked about with airbags because it ties very nicely in, work and energy. And so we determined that work was equal to force times distance, and that the work done in a car crash is going to be done no matter what.
Right.
And so, like in an airbag, we want to decrease the force, but since that value is that value, there's nothing we can do about it. We have to increase the stopping distance. And so what that meant was that the change in energy, or specifically the change in kinetic energy, would be equal to the work done. Impulse and momentum work in exactly the same way. Work can change the energy.
Mm-hmm.
Impulse is the change in momentum. Okay? Of course, things can't be exactly the same. But if we talk about momentum again, from a previous not too distant podcast, we said inertia in motion and we said that the momentum would be equal to the mass of the object times the velocity of the object. Impulse is that change in momentum. So yes, momentum is still conserved. So in the Section 6 podcast and the investigation, we spent a lot of time saying that the initial and the final were the same, and that momentum was transferred from one object to another.
Right.
We spent a lot of time on the left side of the equal sign. We spent a lot of time on the right side of the equal sign. Impulse is focusing on the equal sign. So this is the actual event of the change. So impulse is a change in momentum, so it's delta P. And it's not equal to force times distance, it's equal to force times the time. And so, if I were to finish that, that would be the mass times the change in the velocity. Is it likely that the mass of the object will change?
No.
No. But in a crash, for example, it's really likely that the velocity will change, that there will be a final and an initial.
Right.
And that has to happen over some time, just like it has to happen over some distance. So if you're working on energy as a solution, you have to do work. If momentum is going to be your solution, you have to focus on impulse. So we made this statement way back in podcast 3.1. What do we say? We said longer crashes, less injury, or how about our safer
Okay.
crashes, yeah? And at first that sounds kind of crazy. But let's go back a slide. We already showed with airbags that if you were to increase the stopping distance, you can decrease the force.
Right.
But the amount of work that the car does to stop you
Is the same.
is the same, or your change in kinetic energy is the same. Momentum and kinetic energy are a lot alike, aren't they?
Yeah. What you have is, because you have your change of energy, which was the mass, half the mass times
Right.
velocity squared.
So remember, this was half mv squared. And so if it was a change in, you would do something like that.
Mm-hmm.
Okay? So they both require mass and they both require speed. So once again, up here, the force is still required. If you want to change the velocity of an object, you still have to apply a force. So if it takes more stopping distance, it probably takes more time. And once again, the stopping force goes down. So we are successful by making crashes longer.
And again, it's one of those concepts we talked about in the very first unit where when one of the factors goes up, the other goes down. It's because they're inversely proportional.
Right, inversely related topic. So those are some math words that keep coming back, and not something that's going to go away.
Right.
So we could get bogged down in problems, but I really don't think that that's necessary. Let's go into this just a little bit. How does this work? Well, it starts, like many things in this class, with Newton's laws. And specifically, it's going to start with Newton's second law of motion, which says what?
That force is equal to mass times acceleration.
Right? And so force is equal to mass times acceleration. And we have spent a lot of time on the second law, meaning that if you want to change the motion, that's what acceleration is, change the motion of any object, you have to apply a force to it.
Right.
Okay? So, all right, this causes an acceleration, which is a change in the velocity over a change in the time. Okay? So, remember our triangle means change in, and in this case, velocity. And down here, time. And so what'll happen here, okay, if you stick with me for a little bit, if we multiply everything by delta t, okay, what you determine is that the acceleration times the time is equal to the change in the velocity, or Vf minus Vi. So by applying a force, we cause an acceleration, and that acceleration over some time changes the velocity of the car in this particular case. Okay? So that's really important. And what you see here is how does this all connect to impulse? Okay? Remember, impulse requires a force times some time interval in order to change the momentum, and really what we're changing is the velocity. It all ties together. And that's one thing I really want all the students to focus on as we wrap up the first semester, is that every topic we've talked about relates to every other topic.
Right.
Momentum, force, energy.
Newton's laws.
Sure. Kinematics, graphs. We've chosen to talk about the rules of the road and sports and car safety. We've made that choice, but we don't have to have new rules to fit our new scenarios. The last thing I want to show is the difference between a safe crash and an unsafe crash. So let's start with unsafe. So what do you think? In an unsafe crash, lots of force or little force?
Well, I would think of lots of force if it's unsafe.
Right. So this value peaks way out, which actually you see in the investigation that you do. And in a safe crash, what do we think? Lots of force or little force?
Well, I think it would be maybe like a medium-sized force, but over a longer period of time.
Right. And so something like this. So in your investigation with the computers that we were able to use, what you were able to discover is that the area that I'm coloring in for both of these is exactly the same. And that's really profound, which means that if we go back to our let's make a simpler graph. If we go back to our days of math class, if I want to find the area of this rectangle, what do I have to do?
The slope of the line?
No, the area.
Oh.
What do I?
You have to multiply the sides together.
Yeah, it's just base times height. Well, if my height is force and my base is time, what have I just found? The force times the time. I just found the impulse. So what we have here is we have the impulse. We have the same impulse. The momentum change in the car crash has to be identical, whether it's unsafe or safe. Okay? You're walking away from this one. Okay? Here, you're not doing so well.
No.
Okay? So you saw this, and we did things in the investigation. So we sent the car down a ramp, and there was this force sensor down here, okay, that was measuring stuff. So as the car zipped down, if the car didn't have any padding, it smashed into it. And what did you see? You saw this graph. Okay, so no padding. Or if there was some sort of frilly bumper on the front of it, maybe, and it smashed in, the momentum change was exactly the same, but it's a safer crash because my graph looks like this, and in this case we had padding. It all ties together. So these car safety experts, these safety engineers, they think about all of this stuff when you talk about car safety. So some of the items we talked about in the first section, and we have studied, we focused on seatbelts and how they related to the first law.
Airbags.
We talked about airbags, a relatively new phenomenon, and how they relate to work done on you.
Crumple zones.
We talk about crumple zones in section 7 and how they relate to impulse. By the way, we could have done airbags with impulse or crumple zones with work. It didn't matter.
Mm-hmm.
And then we talked about head restraints with the second law, and actually the first law, and oh yeah, the third law, because it all ties together.
Those seem to be important topics. You think they're on the final?
I think maybe Newton's laws of motion will make an appearance, yeah.
Yeah. Maybe a couple times?
Probably more than once, yeah.
Maybe 3?
Maybe 3. So that wraps up podcast for
First
the
semester, yeah.
So I believe that covers it. Signing off, this is Mr. White.
And Mr. Johnson.